Okay, I think we're ready to start. All right, my name is Dominic Kramer. I'm a software engineer at Google. I work on the Node.js team, and today I'll be talking about how math and JavaScript can be awesome. So for a little bit of background, my research tools of choice in the past when I was in graduate school and before dealt with Mathematica, MATLAB, Python, and LaTeX. Each of these different tools have benefits, each of them have disadvantages, but these are basically the tools I was using. But something was becoming very popular. This something was becoming much more popular after I graduated, and that's deep learning, right? So I'm going to give a very brief overview of deep learning, just a very, very hand-wavy description. There's lots of other talks that have much better detailed descriptions of it. But with machine learning and deep learning in general, what you can think of is you have a big neural net of computations that are going to occur. So for example, let's say you want to make a neural network that does a very important task, which determines if a picture is a picture of a cat or not, right? Well, what you do is you have a vectorization of the cat, and that's shown on the left there in blue dots. And you feed that data to another layer. That layer is the hidden layer. You do some calculations. That layer maybe detects edges. Feeds that data to another layer. It looks at changes in the edges. Maybe it finds round shapes, like eyes or something. And it feeds that layer to the last layer. And maybe that layer just turns a vector into a number, 0 or 1, for no cat or for cat, right? So the key takeaway here is that we're putting data into this system. Let's say data we know. We know there's a picture of a cat. We feed it through the system and it comes back, yes, that's a cat, with a certain degree of confidence. We can use that data to do backpropagation, if it's correct or not, to improve the model. And we do this repeatedly 100,000 times. So the key takeaway is we're going forward, we're going back with the backpropagation, and going forward, basically what we're doing is what's shown on the bottom. We're taking input x, multiplying by a matrix, adding a vector, and then applying a nonlinear function on it. It has to be nonlinear. If it was linear, you just have a big matrix, and it wouldn't be interesting. Right? So this is the key takeaway, that in deep learning, it's really a lot of hardcore math underneath it. And math can be viewed as a collection of tools. Right? Deep learning leverages a lot of these tools. So linear algebra. So a lot of the things that you do moving forward are linear algebra operations. Use optimization theory. For example, gradient descent. So after you get through the process of calculating some value and saying, oh, I think this is a cat or not a cat, you analyze this and say, how good did I do? And to do that, you're minimizing a loss function. And that minimization is using gradient descent or other things. You use calculus, use gradients for calculating, optimizing the system. Use a chain rule. The chain rule is basically what you do when you go backwards. Backpropagation, that's the chain rule that you learn in calculus. And use probability theory. Something like cross entropy, that's the thing that powers the loss function that's used a lot of the time. And deep learning is very, very complicated. There's a lot of things. This is a very rough overview. But the key thing it's just showing is that there's a lot of machinery and mathematics that's used in deep learning. That's mathematics that's been around for a long, long time, and it's used for a lot of different things. And a really interesting thing is TensorFlow.js now exists. So TensorFlow.js is an awesome math library that allows you to run in the browser, lets you run in Node.js, and what it lets you do is build models and utilize mathematics. You can use native TensorFlow. You can use just do an npm install of tfjs node. It'll use the C bindings, so you can using TensorFlow just as it is. Or you can leverage GPUs to get CUDA support. So you have this really powerful platform for doing deep learning that runs in a node, runs in the web, runs anywhere. It takes advantage of hardware. So this is what it looks like, kind of give you an idea. So it's really straightforward. Here you're making a model, adding some layers. That's the layers like you saw in the image. You have your input. This would be like, for example, what the cat picture would be encoded as. And then you do some prediction on it. But the key thing is, that's using a lot of core mathematical tools. And you can directly access those mathematical tools used by TensorFlow. You can build, manipulate, and operate on vectors, matrices, even tensors. And you can do that by just using TensorFlow at TensorFlow/TFJS core. So that's the core fundamental math tooling that TensorFlow is using. And if all you want is the core mathematical tooling, if you don't want to do deep learning, but you still want to access all that powerful math, you can just use this module. And so this kind of gives some examples of things you can do. You can take TensorFlow core and build, here we're doing tf.tensorflow, or tensor2D. We're building a 2D tensor, which is a matrix. And then on that, we're running the Gram-Schmidt process. So that's a process that if you think of this matrix as a bunch of columns of vectors, that makes a vector space if you span all those. This makes an orthonormal version of that, if that's important to you. So the reason this is helpful is this is used in a lot of different things, believe it or not. One thing it's used in is QR decomposition, which TensorFlow also does. And so these types of, and this is a decomposition, you turn a matrix X, which we can see we have our matrix X there. We break it into a Q and an R. Those are two matrices. And it turns out X is equal to Q dot R, which you can see in the very last line. And this is used in lots and lots of different algorithms for doing a lot of different things. So I want to show some examples of, for example, what I would use TensorFlow.js core for. And that is when I was working in graduate school, my dissertation, I was working on something called frame theory. So this is related to linear algebra, real analysis, lots of different things. So it's also related to computer science, which is why I like it. I like both math and computer science. And what I was trying to do was solve this minimization problem. So this looks really scary and like, oh, what's going on here, right? All you got to think about is that you're given an X, a giant matrix that you want to deal with, and you want to find some nice properties about X. So this is a matrix that's taller than it is wide, and that's all you really have to know about. So if I was looking at this and say, I got to figure out how to analyze this problem, what would I do? I think, well, I want to break this into a simpler problem that I can handle. So that's what I'm going to do. I'm going to rewrite this problem into alternate forms until a general problem can be used. So first I'm going to recast it as this problem, and it takes a lot of math to show that you can recast it this way. But the key takeaway here is we got rid of a summation. We had 3 summations before, now we only have 2. So we're making progress. We still have absolute values, but we'll get to that later. And instead of doing a matrix times a matrix, which was what we had before, now we have a matrix A times a vector X. So making progress there too. So now the next step is, well, how am I going to solve this? Like, I don't know how to solve this. But I can recast this into another problem. I can say, oh, that looks actually like this sort of problem. And you don't have to understand what this is. Again, the key takeaway is we got rid of a sum, and we got rid of absolute values. But the even bigger, so this is a simpler thing. The even more important thing is that we can use existing algorithm. That problem is actually a general algorithm for that. It's called linear programming, and it's been around, I think, since the 30s. It's really well known. Before programming was considered programming, because it's before computers existed. There's a simplex method, interior point methods for solving that. And the cool thing is if you broke this problem down into that existing problem, you could be like, oh, hopefully I can go in the ecosystem, do an npm install, and find a package that just does a simplex method, because it's a general algorithm. Unfortunately, that wasn't the case. So I implemented one using the 2-phase simplex method, and I'd like to contribute this back to the ecosystem once I get the bugs worked out. And my hope is that TensorFlow.js, it provides tensors, has really powerful mathematics, it's hardware accelerated, and that these tensors can be a common denominator used for lots of tooling. So if you needed to use some mathematical tooling in your project and said, okay, I need to use matrices, what library should I use? I could use multiple different libraries. I could make my own. You could say, well, I'll work with TensorFlow tensors, and I can start from there. And if I use TensorFlow tensors and make an algorithm that uses them, and somebody else uses TensorFlow tensors to make their algorithm, now our algorithms can work together because we're talking the same language, using the same underlying data structure. So that's kind of the hope. And that's why I want to release my simplex method implementation to kind of get the ball rolling. So I'm going to show you kind of like how this was implemented. The key here, you don't have to understand kind of like why this is. This is turning 2 matrices into a giant matrix. The key takeaway though is just if we want to build a matrix from another matrix, we can just get the buffers from the matrix. That's what the first line is doing, like get the underlying data. Now we're going to iterate through some components of that. And we're going to make a result buffer. This is an array of numbers. And we're going to set the values of that to whatever numbers we want. And at the very end, we build the resulting matrix by just using the tensor2d object. So we take an array of numbers, and we can build a tensor from that. And so step one that we did, we started from the original problem. In TensorFlow.js, all it looks like is this. Using that two-super matrix method or function, all we do is we start with our x. We build a couple identity matrices. It's really easy to do in TensorFlow. You just use the I function. And then you say, oh, we're going to pass those. We're going to use those to make matrices A, B, and a vector C. And we're just going to say, oh, let's let the second step of the problem handle it. So we just pass it to that. And the second step of the problem for handling it, we just take the A, B, and C that we had, and we just make some other matrices. We just kind of move things around and compose things. So we get on the 0m line, we just get an array of zeros. It's a column vector. And simplex B is a vector. We just stack a bunch of vectors on top of each other. Simplex C, we just make another vector. We stack some zeros and some ones on top of each other. And simplex A is a big block matrix, a matrix of matrices. And to build that, we just stack a bunch of rows on top of each other. And to build each row, we stack all the some matrices side by side. So when we say tf.concat2d, give an array of matrices, comma 1, that means stack them horizontally. So we have row 1 through row 4, we stack them all up. And then at the very end to build simplex A, we just stack the rows on top of each other. Right? And if we had a simplex method that was just from the ecosystem already done, we could just do an npm install of that simplex method, and then that would be all our code. That would be everything we need to do to solve that really complicated problem. All the hard work is really in that simplex method, and if that was done by somebody else, you could just leverage it, which is really great. And that's step 3. Just use that. If you can't use it, write it yourself, but then hopefully contribute it back. So this is an example, just kind of show you what this looks like. So this is a problem we're solving. Just pick a random example and do the solution. So this is all running on my browser. And the key thing is, like, I picked a random x, and this is just some matrix that has some properties. And the cool thing that you take away is the solution that I found had 2 columns that were zeros. And the columns that weren't zeros, you look at the corresponding rows in x, and those turn out to have some nice properties. They turn out to be what's called an orthonormal basis. So I can do this with another example. Yeah. So here we have another x randomly generated. Again, the y happens to have this cool property that all the zeros correspond, or have a bunch of columns of zeros, and then the columns that aren't zero and y have rows in x, corresponding ones, or an orthonormal basis. So this is the cool thing I was investigating, that you always have this interesting property. And it's really important, but we don't need to get into details. The key takeaway is that it really was just a little bit of code, if the simplex method was existing in the ecosystem, to get this working. Get it working in the browser, get it working with React, getting working with Node. It was really easy to do if I had that algorithm. So the next thing I want to talk about is, let's say I was working on something and I want to say, like, man, I really want to know, is this number prime, right? Because, like, who doesn't want to know that, right? So this is actually useful. There's lots of ways prime numbers can be helpful. Like if you want to make a prime number, random number generator or something like that, and you say, oh, how can I do this? And you can like look it up. You can look at like the Art of Programming by Donald Knuth. Has lots of algorithms, and for testing if things are probable prime. But you're going to hit a roadblock, and that roadblock is, what's the largest integer JavaScript can represent, right? If there's an algorithm for determining if something's prime, but JavaScript can only determine numbers this big, deal with those, well, that's kind of where your algorithm stops. Unless you want to implement all the logic for making a library that says, how do I deal with big numbers? How do I store those as a list of numbers? How do I describe how to add those, multiply those, do all the testing to make sure it all works correctly? You got to do all that work, and then when you're finally done with that, now you can write your algorithm. But that's a lot of work to do up front. Or is it? So the key thing is, we have Big Int now available in Node 10. I think it's in Chrome 67, V8 6.7, if I remember correctly. And the cool thing is that you can use this just like you use regular numbers, right? So if something like 42n, for example, is a big int. If it was 42, it would just be an integer. But 42n means it's a big integer. Negative 10n, you can just do a bunch of digits in an n. There's a big int function, and that big int function is also something that you can use to generate a big integer. You can give it a number, can give it another big int, or you can give it strings to build things. And like this is useful if you have like a REST parameter. You can have the number corresponding as a string and then pass it to your server. But be careful, right? Because one thing you can't do is mix big ints and other types. Okay? If you try to do that, you're going to get an error saying that you can't, you have to do explicit type conversions. And this is actually really nice because you want to know that you're mixing types up, you're getting things wrong. The problem is runtime errors don't always occur. Okay? So for example, if you said const x equals 42 and said x equals 42, it's going to say, no, those aren't the same, right? Equals, because one's the big integer 42, one of them's the integer 42, and big integers and integers aren't the same. And this is actually, in my opinion, more problematic because you can have some code that seems like it's working, runtime errors, nothing like that, and you can run into problems. Of course, you can use x equals 42, and it'll work fine because it's doing type coercion. So you got to watch out. JavaScript still is JavaScript. And so once we have all that functionality, though, we could actually go back and solve our question, like, hey, how do we tell is this number prime or not? And we can do that by using this what's called a Miller-Rabin primality test. So this is a really cool test. We don't have to really understand how it's working. But the cool thing is that you're given a number m, and it does some calculations to pick some numbers, and it tries to determine those numbers. It picks a number randomly between 2 and m minus 1, and it tries to see if that number is what's called a witness for that big integer m to be non-primed, for it to be composite. If it is, then you know it's not prime. It's not interesting. But if it says it's not a witness, then the number is probably a prime, and the probability it's not prime is at most 1/4. And the key thing is that 1/4 doesn't depend on the size of m. If m had 10 digits, if n had 1,000,000 digits, if 10 had 1,000,000,000 digits, it's still 1/4, which is really helpful, really useful. So to give you an example of that, this is what the function looks like. You don't have to really understand the algorithm or read the code. The key takeaway is that this looks almost exactly the same as what it would look like if you implemented it without big ints. If they were just numbers, it would look almost the same. The only difference is we have an n attached to things. So we say m minus 1n because m is a big int, so we have to subtract away the big int 1, not just 1. But all the other things that we'd like to do are all there. We can iterate in a for loop. We just let j equal the big int 0. We can do comparisons against the big int k. We can add with the increment operator. So everything looks almost identically the same. You have all the semantic sugar or syntactic sugar that you would want. And so this makes writing the algorithm really nice. So to kind of give you a demo of this, this is what it would look like. And the cool thing is, so this is a number we started with. And so we want to say, is this a big int? Do you analyze it? So this has 39 digits, and it's probably prime. The probability that it's not prime is 1 over that huge number. So it's basically prime, right? And what it did is it checked a bunch of these numbers together. And the previous demo I showed you was actually all running in my browser. This could actually all run in my browser too. Because I'm using the newer version of Chrome that has big ints. But this is actually asking the backend server to do some calculation and send it back to the front end to show you that you can actually run it in the backend or the front end, either one you want it to. So interesting note, this number here, I didn't pick it randomly, because if you picked a random number, I'll tell you it's probably not going to be prime. This is the largest known double Mersenne prime. So a Mersenne prime is a special type of prime number. You take a Mersenne prime, feed it into another Mersenne prime to make another bigger number. That's a double Mersenne prime, and this is the biggest one that you can do that they know of. The key thing is you can add a ton of digits, and this thing will just be like, hey, that's cool, I'll do that. So is this number prime? Yeah, so it's 110 digits, and it's probably prime. We can pick another big number down here and say, is this number prime? Like, no. Like, almost immediately it finds what's called a witness. It says this number satisfies some criteria that shows it's definitely not prime. So if you notice pattern, these are all prime. These are all not prime. These are all found via the internet. I didn't figure them out. But the thing I want to show is that if I take this number and just pasted it a bunch of times, so like just pasting a bunch of times, and click Analyze, so that's a number with 2,530 digits, and it's not prime. I mean, I didn't think it would be prime, because that would be pretty amazing if it was, if I just pasted a random number a bunch of times. But the key thing is that's 2,530 digits, And the code that I had was just this code. Oops. It was this code. I didn't have to do anything special to handle those huge numbers. It just handled automatically, which is really nice. So this is this test. And it's showing that you can just handle big integers really nice. The last thing I want to talk about is typesetting. So typesetting might not be as interesting from a computer science perspective, but it's really cool from a math perspective because it lets you draw really cool, pretty mathematics. And normally how you do that in mathematics is you'd write LaTeX code, you'd write it in a text editor, and you'd feed it through a text distribution, and it would make a DVI file. And then we got really fancy, and now we don't use DVIs, we use PDFs because it's really cool. Well, the nice thing is we don't have to use either one of those. Now we can use MathJax, or we can use KTech, which means you can actually embed mathematics directly into websites, into web pages, and it'll either use SVG, it'll use MathML, or whatever it needs to generate things. So this is the example of the thing that I just showed. This LaTeX code right here would look like perfectly normal if you're used to writing LaTeX code. If you're not, it looks very strange. But this is just standard LaTeX code, and it gives this nice description. So this description is a description of what's called the Riemann Zeta-Function. Really important function. There's an unsolved problem. If you can solve it, you'll get $1 million from the Clay Math Institute, probably several awards. It's related to this problem. I picked it because it just looks really cool. Shows the typesetting capabilities. So this is really nice because basically what I showed is I could build now with web technologies, I could build a tool that runs all the way in my browser that shows me all the things typeset in mathematics, runs a bunch of examples on my dissertation problem, and has visualizations, leverages Mocha, leverages React, all these different things make a progressive web app. And I don't have to touch any proprietary code, any third-party code. I can just do everything I want to in a browser. And for example, when I got out of grad school, when I was in grad school, my desktop computer is a computer I use for doing typesetting. When I got out of grad school, my typesetting computer, the computer I was using for doing mathematics was a Nexus 7 because I didn't need anything else. That's the most powerful I needed, and it's all because of these technologies, which I think is pretty cool. So the summary that I want everyone to take away is TensorFlow.js is awesome. Begin's awesome, and typesetting is awesome. But what's important about all these things, not just that you can do things, is that they form the bedrock for powerful mathematics. So being able to deal with fast matrix computations is really important, and having a consistent and a agreed upon tensor data structure that everyone can use is something that can really help build up the community. It's something akin to NumPy. So in the Python community, if you want to write something using matrices, you use NumPy because that's what everyone uses. TensorFlow could be similar. Begin's really useful because now you don't have to do big int operations yourself, which takes a lot of time. And typesetting is awesome because now you can display all these results that you have very easily. And so what I'm hoping is that all these tools can be used to develop general algorithms. So we have the tools now. We have TensorFlow, we have BigInt. What we don't have is the algorithms. We don't have a Simplex method. We don't have methods for doing like polynomial factorization. These are things that are used over and over again in a lot of different things. We don't have those in the ecosystem. But we can have those now because we have the underlying tools to build them, which is BigInt, TensorFlow, things like that. So I'm hoping from this we can have a rich ecosystem of interoperable math tooling, right? So tooling that can leverage the fact that NPM has a lot of small packages to do specific things. If we can have a lot of small packages that do specific algorithms, we can easily build upon that to make a really robust ecosystem. So that's all I want to talk about, and thank you. So I have a few minutes if anyone has questions. Okay. Well, I'll be at the Google booth if anyone has questions. Okay, thank you.